Hi student, welcome to chemistry class with Emerald. This video is brought to you by Igota Virtual Learning. And in this video today, we are going to be looking at elements in a period. Specifically, we are going to be looking at the elements of period 3. Elements in the period 3. If you look at the periodic table here, you will see that the elements in period 3 are sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. These are the elements in period 3. Let's quickly look at how they look like. Um, you will see their different look for elements in period 3. Sulfur is a yellow solid. Sodium is metallic gray. The same thing with magnesium. You can see aluminium also metallic gray or silver color, as the case may be. So you see chlorine, greenish yellow gas, a greenish yellow gas, and argon there. So these are various colors of the elements in period 3. Now, in today's lesson, we are going to be looking at the properties of elements in period 3. These are key properties we are going to be looking at. But in addition to what is here, we also look at their first ionization energy, their melting and boiling points, and then we also look at some critical chemical properties like the nature of their oxides specifically. And then we are also going to be comparing the elements in period 3 and period 2 in terms of their similarities and their differences. Okay, so let's look at first and foremost the electronic arrangement of elements in period 3. You will see that for the proton number, you have sodium 11, magnesium 12, aluminum 13, silicon 14, phosphorus 15, sulfur 16, chlorine 17, argon 18. Those are their proton number. And the proton number can also be known as the atomic number. So this is their atomic number. And then for their electronic arrangement using the K element, so you have 281, 282, 283, 284, 285, 286, 287, and 288 respectively. Key points to note here is that the proton number of elements in the period 3 increases across the period from left to right. And then another thing you should also note that is that the proton number increases by 1 unit from one element to the left to the next. And then the electron arrangement shows that all atoms of the elements across period 3, they have 3 shells. Very important, all elements have 3 shells. Very important to note. Now let's look at the atomic size and electronegativity. Let's look at how they are being arranged in these shells. You will see that they maintain a 2-8. Each of them maintain 2-8. The only difference is that the atomos electron, which is the valence electron, continue to increase by 1 respectively. You will observe that more electrons are being added to the atom as you move increasingly. But interestingly enough, as more electrons are being added, there is no increase in the number of shell. Of course, this will have effect. And what effect will it have? Number one is that the atomic size will decrease. Why is the atomic size or radius decreasing? because the nuclear charge will increase. That means the interaction between the nucleus and the electrons will increase. The nuclear attraction will be will increase, and then the electrons are pulled closer towards the nucleus, because the more you increase the electron, the more the electrons are pulled closer toward the nucleus. So because of this nuclear attraction, the atomic size, the size of the atom will begin to decrease. That means that there will be shrinking of the shell due to high nuclear charge that is there. And of course, because you are adding more electron, and of course electrons are negative, therefore electronegativity will increase while electropositivity will decrease, because you are adding more electrons. So that means as you are moving from left to right, you are moving from metallic character to non-metallic character. You are moving from electropositivity to electronegativity. So electronegativity will increase across period 3. Okay, let's also look at a few of other properties. We have looked at the proton number, we have looked at elements, we have looked at the electronic arrangement. Now let's look at the atomic radius in terms of number. We have talked about the size and the radius in terms of the structure. Now parts per million. Now in the atomic radius here is measured in parts per million. You will see that as you are moving across the period, it is decreasing. So atomic radius decreases. That's the D. That's the one letter D now. 186, 160, 143, 118, 110, 104, 194. 100, and the last one is 94. You observe that the atomic radius is decreasing, like we have said, due to the increase in nuclear charge, and then because the electrons are pulled closer towards the nucleus. Again, let's look at the physical state of elements in period 3. You observe that you are moving from solid to gas. Most of them are solid with the exception of chlorine and argon, which are gases. So all other ones, sodium is a solid, magnesium is a solid, aluminum is a solid, silicon is a solid, phosphorus is a solid, sulfur is a solid. Only chlorine and argon are gases. Please take note of that. And then in terms of value now, again, let's look at the values of the electronegativity. Like we have said, it is increasing across the period from left to right of the period 3. You have 0.9, 1.2 up to 3.0. Of course, argon does not have electronegative value because they are inert. It's an inert gas. That is why it's not having electronegative value. Okay. Now, let's do a summary of across period 3. The proton number increases. All the atoms of the element have 3 shells occupied with electrons. The number of valence electrons in each atom increases from 1 to 8. All the elements exist as solid except chlorine and argon, which are gases. The atomic radius decreases. This is due to increasing nuclear attraction on the valence electron. The electronegativity of elements increases. This is due to increasing nuclear attraction on the valence electron and the decrease in atomic size. So this is a summary of what we have said so far. Now let's look at interesting part of these elements in period 3. They all form oxides, but their oxides have basic characteristics. For instance, sodium can form sodium oxide, although sodium is able to form more than sodium oxide. Sodium can form sodium peroxides and sodium superoxides. It's only sodium that can form this peroxide and super oxide. Okay, so you have sodium oxide there, you have magnesium oxide, you have aluminum oxide, silicon oxide. We can have that silicon oxide, you have phosphorus, you have sulfur. Of course, sulfur can form SO2, sulfur 4 and sulfur 6 respectively, and then you can have chlorine also forming oxides. Phosphorus can also form P2O5, that's phosphorus pentaoxides. Of course, silicons can also form silicon 2, silicon 4 oxide, and then silicon 2 oxide, SiO and SiO2 respectively. Please take note of this. And then the interesting part of the oxide is that as you are moving across the period 3 from left to right, you have basic oxides for sodium and magnesium. Aluminum is able to form amphoteric oxide. The implication is that this oxide can react with both acid and base. Under types of oxide, basic oxides are oxides of metals that dissolve in water to form a base. So when you dissolve sodium and magnesium oxide in water, they will form an alkali or a base. But aluminum oxide, when you dissolve in water, can form both acid and base respectively. While acidic oxide are oxides of non-metal, and as such will dissolve in water to form an acid. Also take note that the elements in the period 3, we are moving from metals. Sodium, magnesium, aluminum are metals. Silicon is a semi-metal, and while phosphorus, sulfur, and chlorine are non-metals. Please note that argon will not form oxide. Like we have said, argon is an inert gas, and they are chemically less reactive, so they don't partake in all of these things we have mentioned. So we will talk about the implication of being metals. That means metallic character decreases across the period from left to right, while non-metallic character increases in this period 3 that we are looking at. All these are very, very important. Okay, so let's look at this more. The oxides of elements change from basic to amphoteric, and then to acidic. Metal form oxide with basic property like sodium oxide and magnesium oxide. The basic oxide can react with acid to form salt and water, like we have said. So you will see that the magnesium oxide being formed there now, that we see there, can react with an acid with HCl to form salt and water respectively. The amphoteric oxide here can react with both acid and base to form salt and water. An example is aluminum oxide, which is amphoteric. It will react with acid to form salt. It will also react with base to form salt and water respectively. The non-metals will form oxide with acidic property. For instance, sodium SO3 can react with H2O to form H2SO4. Like we have said, argon as a noble gas does not form any of these. Okay, so let's look at the properties of the oxides that these elements in period 3 forms. If you look at sodium oxide, it will when sodium oxide reacts with water, it forms a soluble solution which is colorless, and the pH value is around 13 to 14, which makes it basic. And then the sodium oxide can react with NaOH. It can react with NaOH to form insoluble, and then can also form a soluble colorless solution with HNO3. That shows that it is a strong base and or a strong alkali. The same thing with MgO, magnesium oxide, 8 to 9. So the pH is 8 to 9. That means it's slightly alkaline. The MgO is slightly soluble, and then of course with NaOH is soluble. With HNO3 it is soluble and forms colorless solution. Aluminum oxide is insoluble in water, forming a pH of 7. But with NaOH it forms a soluble colorless solution with HNO3 forms a soluble colorless solution. That means it's an amphoteric oxide because it forms both acidic and basic property. The SiO2 is insoluble in water with a pH value of 7. That means it will react with, and of course it will react with NaOH to form a soluble colorless solution, but with HNO3 it will not react with HNO3. That shows that it is an acidic oxide. And the same thing happens to the P4O10, SO2 and Cl2O7 respectively. You can look at it. Yeah, so the oxides of elements in PO3 is changed from basic to amphoteric and then to acidic as we move from left to right of the PO3 elements. Okay, we can predict the changes in the properties of elements across other periods. To summarize their properties again, the elements changes from solid to gas, from metals to non-metals, from conductor to non-conductor, and then the properties the properties that decreases from left to right, the atomic size, the melting points, and the boiling point. You will observe that under boiling points, let's make a very good statement here. The melting and boiling point will increase then decrease. Please let me this must be very clear. The melting and boiling point of elements in PO3 will first increase because you are moving from sodium, which is in group 1, to magnesium to aluminum. Generally for metals, melting and boiling point increases. So between sodium, magnesium, and aluminum, there is an increase in melting and boiling point. So aluminum has the highest melting and boiling points due to the presence of a metallic character. Metallic character increases in between them from sodium to magnesium. Metallic character increases, so they have high melting and boiling point. And of course, as you are moving to group 4 also has a very high, a very strong covalent bonding. So they have very high melting and boiling point. As the case may, as seen in carbon, for instance, with its allotropes, diamond, having a very strong melting and boiling point. But as you now move from group 5 to 7, we are looking at this is we have simple covalent compounds. They have simple covalent compounds, and as such, they have low melting and boiling point. So the melting and boiling point between group elements in PO3 will first increase from sodium to magnesium, then to silicon, then start decreasing when you get to the elements in the group 5 out of them, which is phosphor, because they have simple covalent bonds. So you are moving from, even in terms of bonding now, you are moving from ionic to covalent, then to simple covalent compounds. Now the properties that will increase from left to right will be the proton number, the number of valence electron, and the electronegativity. Please also note that the first ionization energy also increases. Please take note of that. The first ionization energy from left to right of the elements in PO3 increases. Why? Because electrons are held tightly by the nucleus and becomes harder to remove. The electrons are held tightly and becomes harder to remove. Now quickly we will look at the similarities between PO2 and PO3. Let's look at the similarity between them. If you check PO2 and PO3, there is relationship between them. Lithium and magnesium have a very strong relationship. Beryllium and aluminum has a very strong relationship. Boron and silicon the same. Carbon and phosphorus the same. What's this relationship called? It is called diagonal relationship. We have talked about this before. A diagonal relationship occurs because crossing rightward and descending the periodic table have opposite effect. When you are crossing rightward and descending the periodic table have opposite effect. So boron and silicon, for instance, they are semiconductors. They will form halides that are hydrolyzed in water and have acidic oxide. For lithium and magnesium, for instance, they will form normal oxides. For instance, lithium do not form peroxide and superoxide that sodium and potassium will form. So both lithium and magnesium forms normal oxide. They both form a stable nitride. They both form a stable nitride. That's lithium and magnesium. And then again, they both form covalent organometallic compounds. They both form covalent organometallic compounds. And of course, their chlorides are deliquescents. So these are more similarities between lithium and magnesium, and the same for others. So between group 2 and 3 we have diagonal relationships, and this shows that between these diagonally placed elements, they have some interesting similar chemical properties. Okay, let's look at the difference between period 2 and period 3 elements. If you look at period 2 and period 3 elements, period 2 have less metals. You can check, only lithium and beryllium are metals, others are metalloids and non-metals respectively. But if you check period 3, you have about 3 metals. So period 2 have 2 metals, period 3 have 3 metals. That's sodium, magnesium, and aluminium. That's number 1. Number 2, all the elements can form the atomic molecule in period 2 except beryllium and neon. And why? Because beryllium is a metal, it cannot form the atomic molecule. And then of course, neon is a noble gas, but all others can form the atomic molecules. But that means that in period 2 we have more diatomic molecules, but in period 3 we have more of polyatomic molecules. They form they are polyatomic molecules. Another difference between them is that period 2 have less stable isotopes. They have less stable isotope. For period 3, all the elements, they have more than one stable isotopes. They have more than one stable isotopes. You can talk of for instance, magnesium, sodium. You have sodium 11, sodium 1123, sodium 1124, and the like. So they have, each element in period 3 have more than one stable isotopes. This is a key difference between them. Okay, we have mentioned semi-metals here, or metalloids. These are key properties you should know about them. In the period, you have and their uses. These are key properties. Semi-metals, they are weak conductors of electricity. You have silicon here, you have germanium here, and they are used as semiconductors. Semiconductors are used to make diodes and transistors, and they can be used to make microchips. Okay, these are the uses of semi-metals in industry. Because we are putting it here because I'm putting it here because they are mentioned a lot in this video. Now let's look at few WAEC questions. WAEC 2013, for instance, the element with electron configuration 1s2, 2s2, 2p6, 3s2, 3p1 belongs to. The first thing you do is to calculate the atomic number. From here now you have 2 plus 2 plus 6 making 10 plus 2 making 12 plus 1 making 13. That means they are talking about aluminium here. Aluminium is in period 3 like we have mentioned, and in group 3, and because it's ending with P, definitely is a P block element. So the answer is D. The answer is D. Okay, let's look at and that's aluminium there for you, and that's the answer. Okay, so let's look at question 2. WAEC 2014, you have to consider elements magnesium and aluminium again, which is 13. Sorry, that's 13, magnesium 12, and aluminum 13. You have to write the electronic configuration and explain why the force ionization energy of 12 is greater than that of 13. Let's look at it. This is the electronic configuration, and then the second question is that the 3p electron in aluminum is slightly further away from the nucleus than the 3s electron of magnesium. So the screening or shielding effect is more in aluminum than in what? In magnesium. So these two effects outweigh the increase in nuclear charge. Hence, the nuclear attraction of 3s is greater than that of 3p. Is greater than that of 3p. And then of course there is another way to answer it there. So these are possible answers you can give to that question. Let's look at WAEC 2014 once again. In our question, the question says you have to write the formula of 3 different oxides of PO3 elements that react with water. So these are oxides of PO3 elements that can react with water. You have to write answer, put 3 there. So we have sodium oxide, magnesium oxide, phosphorus oxide, sulfur 6 oxide, chlorine oxide, sulfur 4, and sodium peroxide respectively. So you have to put 3 there. 3 of that reacts with water. Okay, the final one will be WAEC 2017. Which of the following arrangement indicates correct decreasing order of ionization energy of PO3 elements? The decreasing order of ionization energy of PO3 elements. The answer is B. Why is it B? You have chlorine, phosphorus, aluminium, and sodium. Ionization energy will increase from left to right across the PO3 elements and decrease from right to left across the same PO3. So that means that chlorine has the highest ionization energy, while sodium will have the lowest. So these are answers to some of the WAEC questions in this model. So far so good. We have looked at the period 3 elements, and then we have been able to establish different parts. We have looked at the differences between period 2 and period 3. We have looked at the similarities. We have looked at some of the properties that increases the proton number, valence electron, electronegativity, and ionization energy. We have looked at properties that decreases atomic size, atomic radius, melting and boiling points. We have looked at them. We have looked at some of their properties from solid to gas, metal to non-metal, and then we have looked at the properties of their oxides, the oxide that they form. We have looked at how they form metal, semi-metal, and non-metal. Of course, and we have established that we are moving from ionic to simple to covalent, then to simple covalent compounds. We have looked at their various properties in terms of their numerical value. And this is the end of, and of course we have looked at how the elements look like and their electronic configuration. So this is the end of the topic. do what to go through it over and over again and solve other questions relating to periodic table of elements in period 3. Thank you for watching and keep learning chemistry.